All right, good afternoon, guys. So we will spend some time going over any questions that you have from the homework. Then we have a very short quiz. I would suspect that the quiz is going to take will take around 5 minutes. It's not a very lengthy thing. The basic idea here is that we've kind of focused everything around trying to determine slopes of tangents from the very beginning. Even though we weren't talking about tangents right away, everything you learned was done that way in the course so that you could eventually find the slope of a tangent. So when it comes right down to it, you have to be able to find the derivatives of any of these functions that we're looking at up here. And remember, the derivative is simply another function whose purpose is to find the slope of the tangent at any particular point to the function whose derivative you're looking at. As well as having the ability to find derivatives, now you have the ability to find equations of tangent lines. And that really is what the quiz is about. So to pick a quick example here, if we were to choose C, and I said to you, determine the equation of the tangent to this function. The function is y is equal to x plus 6x to the negative 1. And the point of interest is 2, 5. You could certainly do it by taking a secant slope and having one endpoint of the secant slope approach P and treat it as a limit. But we learned yesterday that to differentiate this function, you can use what we call the power rule. dy dx is just the notation that we can use for the derivative of the function. So you swing the exponent down in front of the variable. The base remains the same. You drop 1 from the exponent. We swing this exponent down in front and multiply by the 6, and you get negative 6. The base remains the same, and you subtract 1 from the exponent. So what you end up with for a derivative is the derivative of this function is 1 minus 6 over x squared. And what that is a tool that allows you to find the slope of the tangent to this function, to the original function, wherever you want. So if you want to find the slope of the tangent at 2, 5, the slope of the tangent will be the derivative at x equals 2. It's that simple. You're going to put 2 into this derivative. You'll have the slope. So the slope of the tangent will be equal to 1 minus 6 over 2 squared. And, I mean, you can work out what this is. The slope of the tangent will be equal to 1 minus 3 halves, which I believe works out to negative half. Can anybody give me a thumbs up on that? Good stuff. So now if you want to find the equation of the tangent, you know the point, you know the slope. The rest of this is a grade 10 kind of question, but that doesn't diminish the importance of being able to do it. You go y minus y1 equals the slope times x minus x1. So we would have y minus 5. It was 2, 5 equals the slope. We got negative 1/2 x minus 2. You know, expand that through. We'll finish this one off. You'll get y. Actually, what I would probably do because I don't like fractions in my equation, I would multiply the y minus 5 by 2, so I don't have over 2 here. I just have negative 1 times the x minus 2. That gives me negative x plus 2. And I have 2y minus 10, so your equation is x plus 2y minus 12 equals 0. Okay. All that being said, does anybody have any questions from any of the homework? Hayden? 3B? Yeah. Okay. All right, so we have 7 root x minus 3x at 1 comma 4 is the point. Yep, that's right. I just wrote the root x as x to the half because we need to think of it as exponents. Now, some of you might leave it as root x, but when you find the derivative, you're certainly going to be thinking of it as a half. So the derivative here, dy dx, would be 7 halves x to the negative 1 half. You know, I will no longer write what I wrote in the previous example, which is that. When it's just a number in front of x, we know the derivative is going to be that number. After we swing that 1 down enough times and write x to the 0, we say x to the 0 is 1. The bottom line is the coefficient is the derivative. So we don't need to do that. So now what we want to do is use that to find out the slope of the tangent when x equals 1. So I'm simply going to put 1 in for x. You know, I would normally have moved that negative exponent to the bottom and said over a square root, but putting 1 in, 1 raised to any number is still going to give you 1. So what we get is 7 halves minus 3, which is 1 half, I think. Yeah, 1 half. So this works out to a slope of a tangent of 1 half. And now we can go y minus y1, which was 4. It was 1 comma 4. Yeah? Equals the slope of 1 half, which we figured out, times x minus the x coordinate. And again, I just prefer to... by the way, I really don't like having equations this way in this course when we're finding equations of tangents. I would much rather... I mean, I'm kind of indifferent to this. It doesn't matter. But I would much rather have ax plus by plus c equals 0. And when you use this, I think this is called standard form, you don't want fractions ever. Since it's equal to 0, if you do have fractions, you get rid of them by multiplying everything by whatever's necessary. So I would multiply both sides by 2. And then just be left with x minus 1, and I basically have my equation now. Is that good?
Yeah. I don't know why I got like 0.5 when I put the 1 to the negative 1 over 2. I just must have been calculating something wrong somehow.
Well, 0.5 is the slope.
No, but like I would put 7 over 2. Like I did the 7 over 2 thing with the exponent, and then I would get 7 over 4. And I kept doing it. I was like, what's going on here?
Okay. And by the way, this isn't quite done. You're going to write x minus 2y plus 7 equals 0. Any other questions? Enrico?
1g.
1g? On Monday, during Monday's lesson, we will learn how you could differentiate this without using the power rule directly. And all you know right now is the power rule. And the power rule only works if you have a number times the variable that you're differentiating with respect to raised to a number. Okay. What we can do here is something we're going to be doing later today after you write your quiz. It's a very important idea that you very rarely do in high school math until you get to higher levels. And what we're going to do is we're going to take this, I want to rewrite it. I'm just going to rewrite this as x plus 1 over x to the half. And what we can do is rewrite this as x over x to the half plus 1 over x to the half. We normally take two fractions like that, like a over b plus c over b, we put a plus c, right? We normally bring them together. Here we're going to separate them out. What that's going to allow us to do is we will write y equals x to the 1 over x to the half plus 1 over x to the half. And each of these two terms, Enrico, can be written as a number times x to a number. We can subtract the exponents here, which is a property of exponents. 1 minus a half is a half. So we end up with the first term being x raised to the 1/2. And then this guy, we're just going to move that power on the bottom to the top and write it with a negative exponent. That's your negative exponent rule. Now I can find dy dx. 1/2 x to the negative half minus 1/2 x to the negative 3/2. And I'm really not interested today at all about how to simplify this. It's important, and it's going to involve factoring, and when the time comes, we'll do so.
Right, so on equation, it's not going to matter?
No.
Right.
Hayden.
I brought the square root of x to the top and I multiplied it in, and I had like the x plus 1 in that fraction. Is that like a fluke, or will that work?
Absolutely, yeah. So what Hayden is saying, and it's probably what I would have done, to be honest, is I would have thought of this as x plus 1 divided by that. So that means y equals x plus 1 multiplied by x to the negative half. So what Hayden did is he multiplied x to the 1 times x to the negative half. By the way, when you do that, you get x to the half. Yeah. And then 1 times x to the negative half gives you x to the negative half. So it's the same destination we end up with, and that's fine. Any other questions? Yep.
Is there any way to find the domains without graphing it?
Yeah. I'm not really too picky about this. I didn't talk about this yesterday, but it did talk about, what are the domains of the derivative, I think. When we take a look at the derivative, and you do need to simplify this to find the domain. So I guess we'll spend some time doing it. There are ways for you to bring this together. Simplified means single fraction. Something with no negative exponents over something with no negative exponents. So there is a way that you've been taught all throughout your algebraic career, and it would be to do this. And find a common denominator, which is really not what we should be teaching you. There's a better way to do it. And the better way to do it is to factor this. Both of these terms have a half, and we're going to factor out the lowest exponent. The lowest exponent is x to the negative 3/2. So what would we have left? Well, we would have the half is gone. We would have x raised to an exponent, which when added to this exponent gives you 1/2. Negative 1/2, rather. So I want to get to negative 1/2, and I'm adding some number to negative 3/2. I have to add 1. That means I'm left with x to the 1, and then I factored the whole thing out, so I'm left with that. And what that tells us is that the derivative in simplified form has an x minus 1 on the top and a 2 times x to the 3/2 on the bottom. And that's what you would get if you would have looked at this stuff in red and found a lowest common denominator. Then you could say, oh, the domain is x. Well, there's a little bit more involved here, Miriam, because on the bottom you have x to the 3/2, which is that. Now, x, when you take the square root of something, what we would normally say is x must be greater than or equal to 0, wouldn't we? Except that it can't be equal to 0 in this case because it's on the bottom. And if it's equal to 0, then the bottom becomes 0. So it has to be greater than 0, so you're allowed to square root it, and it can't be 0 because otherwise you're dividing by 0. The domain is unimportant here right now. It really has nothing to do with anything. what you've done in this particular question is you've said that the derivative of this whole thing, dy dx, is the derivative with respect to x of 5x squared minus the derivative with respect to x of 7x. You probably don't write that, and nobody does. But what we're saying is the derivative of a difference is the same as the difference of the derivatives. That was one of the rules we talked about yesterday, and the same is true for the sum. We're going to determine right now whether that's true for products. That is to say, if we take the product of something and differentiate it, will we get the same thing we would get if we differentiated the first part and differentiated the second part and then multiplied? Do you understand the difference here between the derivative of a product and the product of a derivative? Okay, in one case, the derivative of a product, you take the two things, you multiply, and then you find the derivative of that. In the other, the product of the derivatives, you take the derivative of this and the derivative of this and multiply. And that works for sums and differences. Does it work for products? Well, the answer is going to be no, but let's show you an example of a case that illustrates that. One of the functions is 3x, one of the functions is x squared, and we are asked to determine the derivative of the product of the two functions. Now look very carefully at the notation here. They are saying we're going to take the derivative with respect to x of the product of f of x and g of x. Well, since that 3x multiplied by x squared is inside of brackets, that means we have to multiply it first. That's the order of operations. And then that operation on the outside, which is a differentiation operation, happens next. What this works out to is the derivative with respect to x of 3x cubed. So I'm just simplifying this by adding the exponents, and that really is child's play. I mean, you swing the 3 down, you drop 1 from the exponent, you get 9x squared. So the derivative of the product is 9x squared. Okay, could we have just found the derivative of the first part of the product and the derivative of the second part of the product and multiplied them? Well, let's see. Part B says, what's the product of the derivatives? So this means, let's take the derivative with respect to x of 3x and multiply by the derivative with respect to x of x squared. And by the way, the value in doing this warm-up is not just related to the product rule. The value in doing this is getting you more accustomed to that notation. So the derivative of 3x with respect to x is 3, multiplied by the derivative of x squared with respect to x is 2x, and 3 times 2x is 6x, which isn't what we got when we found the derivative of the product. And that's the overriding lesson here, is the derivative with respect to x of a product of two things is not the same as the product of the derivatives of the two things. And it turns out there's a rule for finding the derivative of a product. And this is what we're interested in here. See, because eventually, and you don't need to write this down, but eventually you're going to be seeing functions that look like the following. Okay? You're going to be expected to find the derivative of something like that. And if all you rely on is the rule we learned yesterday, which is every term has to be number x number, then you're going to have to take 2x squared plus 11x, and I don't care whether you know the binomial theorem or not. Nobody wants to expand that out raised to the 10. And then to boot, you're going to multiply it by 4 minus x a couple times. So what you're going to end up having to do is find the derivative of this product. And you have to know the rule. There's something we can do with this and this so that we do get the derivative of the whole thing. And that thing that we do is called the product rule. The product rule is something you will get very, very used to. Let me just say it in words. And I haven't used the product rule once since last year in this course. The derivative of a product can be found by taking the derivative of the first multiplied by the second plus the first multiplied by the derivative of the second. It's almost kind of a rhythmic thing. The derivative of the first times the second plus the first times the derivative of the second. And that's what this is saying. This is probably the simplest way to write out the meaning of the product rule. Fg quantity prime, which means the derivative of the product of f and g, is equal to f prime g plus fg prime. I don't use that notation. I don't like using function notation without an x, usually. I hate using this. This is really, really cluttered and confusing, but it says the same thing. The derivative of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. I do like, I take it back, I do like this. It's nice and easy. It's just that it doesn't have the x in it. And derivatives are always with respect to a variable. And if you have an equation that has x's and r's and p's in it, and you use this, we don't know what the variable is. There's no reference to it. I do like this, but notice how I wrote it. I wrote it a little bit different here. The way I say the product rule is derivative of the first times the second. Do you understand that this is the same as the derivative of the first times the second? From here to here is d first, and this is second. It's just written that way because if you write d dx of f of x times g of x, you might think it means this, and that's not what it means, okay? And I will tell you right now, and your author has written a lot of calculus books, this seems to be the only one where he has decided to switch these two. And the order in which you add doesn't matter. It really doesn't. So when you look in your textbook, what the author will say is that the derivative of f times g is g prime f plus f prime g. Do you get the idea that when we look up at this, the order of these two doesn't matter, the order of these two doesn't matter, and the order of these two doesn't matter? Because, as you learn in Math 30 with orders of operations with functions, sums and products is not order dependent. It doesn't matter the order you do them in. Okay? And I would like to prove this to you. You don't have to write down this proof. You certainly can. There are other proofs available. This is the one that I typically use. If a function y is equal to f of x times g of x, two other functions multiplied together, then let me write out your derivative definition. I'm going to need to actually call this function something else. I'm going to call it h of x. Okay. The derivative would be h of x plus h minus h of x all over h as a limit, right? This shouldn't be a big shock to your system. That's how you find a derivative, right? Are you with me here? Or have you got the Friday afternoon snoozes? You're with me, okay. So what would this be? This would be the limit as h approaches 0 of f of x plus h g of x plus h minus f of x g of x. And I'm going to leave a big space here. because I'm going to do something, and I don't know who came up with this idea for this proof, but it's pretty brilliant. I'm pretty sure I wouldn't be able to come up with it on my own. Somebody somewhere along the way worked at this for a very long time and thought, well, how can I figure out what this is? And they decided that what they would do in here is they would subtract g of x plus h f of x and immediately add g of x plus h f of x. Why? Because they tried doing things and they put something in and they did a bunch of work and nothing happened. It didn't work. And they tried putting something else in and they did the same thing. Now what we're going to do is the same thing that we were talking about with that 1 plus root x all over root x, where we split the two pieces into two fractions. So I am going to write this piece as a single fraction plus this piece is a single fraction. So what I'm going to get is the limit as h approaches 0 of f of x plus h g of x plus h minus g of x plus h f of x all over h plus g of x plus h f of x minus f of x g of x all over h. And I'm going to recognize that I'm taking the limit of the whole thing. Now, just want to make sure I wrote everything correctly. Okay. Now, you remember when we first learned limits and then I put up from page 13 of your textbook all these rules for limits? And I said, really, we don't need them to evaluate limits, but we will need them later. One of the rules was this. The limit, and it doesn't matter what is approaching what, I'll just say as x approaches a, of r of x plus s of x is the same as the limit as x approaches a of r of x plus the limit as x approaches a of s of x. Right? And I'll give you a reason why we use this limit rule to begin with. If I said to you, what is the limit as x approaches 2 of 2x cubed minus x, when you put the 2 here and here, what you're doing is you're finding this limit and you're finding the other limit, and you're subtracting them. And what that means is I can write this as the limit of this thing plus the limit of that thing. And I'm going to do that, but at the same time, I'm going to factor out of the top of this first limit g of h plus x, or g of x plus h. So now I have g of x plus h multiplied by f of x plus h minus f of x all over h. And by the way, that should look familiar. Plus, this will be the limit as h approaches 0, and I'm going to factor f of x out of this. So then I'll be left with g of x plus h minus g of x all over h. I guess I don't need that bracket. One of the other rules for limits was the limit of a product is the product of limits. And I'm not going to write that out, but basically that's why if you want to find this limit right here, it's equal to 2 times 2 cubed, because the limit as x approaches 2 of 2 times the limit as x approaches 2 of x cubed gives you 2 times 2 cubed. Okay? And this gets very confusing, but this is the idea behind a proof. What I can now do is I can write this part as the limit as h approaches 0 of g of x plus h multiplied by the limit as h approaches 0 of this beast plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of this beast. So I haven't done anything. This is a long process, right? But I don't think I've done anything that you're looking at going, what did he do there? I've explained every step, and you should follow it. Now, can you evaluate this limit? Well, yes, you can. You just put h equals 0 in. So that limit is equal to g of x plus 0. Can I evaluate this limit? Well, I'm not going to evaluate this limit. This limit is the derivative of f of x. It's f prime of x. Right? F of x plus h minus f of x all over h taken as a limit. When h approaches 0 becomes the derivative. Plus, and I think most of you can see where we're at here, this doesn't even depend on h. So if I put h equals 0 in, I get f of x. Right? It doesn't even depend on h. This, the limit as h approaches 0 of g of x plus h minus g of x all over h, is the derivative of g of x, which is called g prime of x. So look what we're left with. We're left with f prime of x times g of x plus f of x times g prime of x. We're left with the derivative of the first times the second plus the first times the derivative of the second. And those of you that are going to be taking calculus in post-secondary, when your prof gives a lecture on the product rule, he or she will spend most of the time doing the proof and very little time doing examples. And that's kind of what you end up spending a lot of time with in post-secondary. Now, regardless, in the end, that's the product rule. You're not given it for exams. You're expected to know it. Let's take a look at some examples now. So when I look at this thing in example 1, where we're asked to find the derivative of this function, which is a product, the first thing that pops into my head is FOIL the thing out, and then you don't have to use the product rule, right? And I'm going to do so off on the side. You can write this down if you want or not. If I FOIL it out, I get 12x. I get a negative 9x squared. I get minus 8, and I get plus 6x. My brain doesn't go very well when the x's are mixed up like that, when they're not x then number. But can you confirm those are the 4 terms? Okay, so that means that y, if we were to FOIL it out, is negative 9x squared plus 18x minus 8. So can I get everybody to double check my algebra there? I just want to make sure it's good. Okay, so if you did that, the derivative could very easily be found without even referring to a product rule. And I would say, even though you only officially learned this power rule yesterday, the power rule is what we're using to do this. It should be like second nature almost. You shouldn't even really be thinking too much about it, which can be a bad thing because you might be on autopilot and make mistakes. Are we in agreement that's the derivative? Most likely you would probably factor and write the derivative that way. But anyway, that's the derivative. What I'm about to show you with the product rule is very messy compared to this. So why are we doing it? Because eventually I'm going to put exponents like this on the top. And the prospect of multiplying stuff out is lost. I mean, you just don't even want to consider it. So we have to get used to the product rule first. So dy dx will be equal to, now I'm going to write this out first. And then I'm going to dissect it for you and explain what's going on. This is the derivative of the first. This is the second. This is the first. This is the derivative of the second. So that's what's going on here. Your prof or instructor in post-secondary, when you first learn this, is most likely to write the following. And there's absolutely no reason for you to write it, but you should understand its meaning. What your prof or instructor is likely to do is say dy dx equals d dx of 3x minus 2 multiplied by 4 minus 3x plus 3x minus 2 multiplied by d dx of 4 minus 3x. Do you see what's going on here? I only offset things here vertically because if I put this 4 minus 3x up on the same line up here, you might think that it's the derivative of both. And there's nothing wrong with putting it up there as long as you do this. Right? There's no need for brackets over here because that thing is out in front. It's almost like a coefficient. So then what your instructor would say, what is the derivative of this? It's 3 times that plus this times what's the derivative of d of 4 minus 3x? Negative 3. And now you multiply this out. So if I multiply this out, what do I get? dy dx is equal to 12 minus 9x minus 9x plus 6. And it doesn't take, a PhD in math to realize that you're going to get the same thing. Right? Negative 9x and negative 9x is negative 18x, and then you have 18. So that's the answer. Negative 18x plus 18, or 18 times 1 minus x, or negative 18 times x minus 1. Lots of ways to write it. Questions with number 1? Okay, number 2, if g of u equals 2, u to the half, let me write this out, g of u equals 2, u to the half times 3u squared minus 2u minus 3, what's g prime of u? Well, there's nobody in the world with any real skills in math who would use the product rule here. You'd multiply that term through, right? But we're going to use the product rule because we're learning about it. So g prime of u will be equal to u to the negative half times 3u squared minus 2u minus 3 plus 2u to the half times 6u minus 2. So again, I will dissect that because after you get somewhat skilled at this, as I say, your mind goes on autopilot and you really just start writing and thinking and doing the math all at once. This is the first and this is the second. So the derivative of the first is found by swinging the half down in front. 1/2 multiplied by 2 gives you 1. And then I drop 1 from the exponent. When I subtract 1 from 1/2, that's where this negative 1/2 comes from. This negative 1/2 comes from the fact that you're taking the positive 1/2 and you're subtracting 1 from it. and then multiplied by the second, which is 3u squared minus 2u minus 3. Then the product rule continues and says now we add the first, which is 2u to the half, times the derivative of the second. The derivative of the second is the derivative of this thing, which gives us 6u minus 2. Are we in agreement? This is really frustrating for me and probably for you, because now you got to multiply this all out anyway. So, it would have been so much easier had we just multiplied it out to begin with once and then got the answer. But we're doing this so we can learn about the product rule. When I multiply this out, I'm adding exponents. So I'm going to do this, and then we will double check. I think that's what we get. I have some terms which are similar. I have 3u to the 3 halves and 12u to the 3 halves, which is 15u to the 3 halves. I have a couple of u to the halves. Well, I have 6 of them. Negative 2 and negative 4 is negative 6u to the half. And I have a lowly negative 3u to the negative half. Okay, well, it's time to start getting used to factoring answers. Are we okay with those 3 terms? We have 3 terms. Is there a common factor? Well, yes, there's a common factor of 3, and there's u's in everything. So what do we factor out? U raised to the negative 1/2, always the lowest exponent, which means our derivative becomes 3u to the negative half. What do we have left? We have a 5u squared. Because 2, and you can correct me if I'm wrong, 2 is the number that I add to negative 1/2 to get 3 halves. That's correct. I'm thinking number line here. Here's negative 1/2. We want to get to, this is 0, this is 1/2, this is 1. We want to get to 3 halves. You've got to add 4 halves, which is 2. I take the 3 out of the 6, I'm left with a 2, and it's negative, and I will have u. And then I take out the whole thing, and I'm left with 1. This is very common, by the way, for after you factor some weird stuff out to be left with something that's like grade 10, 11 expressions. It's quadratic. I don't think that's factorable, though. You can do the b squared minus 4ac thing. I'm pretty sure it's not. You get 24 for b squared minus 4ac. So it's not factorable. So we're done. That's the derivative. Oh, actually, no, we're not quite done. This is the derivative. I don't want to get into the depth of it again that I have in the past today because we don't have time, but very important that you write all answers as a single fraction, where the bottom is factored as much as possible and the top is factored as much as possible. The 3, by the way, is not raised to a negative exponent. It stays on top. Yeah?
You prefer u to the negative 1/2 over root u?
Can you repeat that, please?
Is u to the 1/2 preferable to root u?
Doesn't matter.
Okay.
I mean, I have a preference, and it's to use an exponent. Because anytime I have to do something mathematically, an exponent is a number. I know what to do with it. When I see cube root times 4th root, I immediately think raised to the 3rd times raised to the 4th. So it's up to you, though. Next question, number 3. What's the equation of the tangent to the function given here at x equals 2? So we need to find the derivative of this. And we could FOIL it out, but I'm going to show you why we don't want to FOIL it out in this case. It wouldn't be easier to FOIL it out first. The derivative with respect to x, which is going to lead us to the slope of the tangent, will be 6x minus 2 times x minus 3x squared plus 3x squared minus 2x times 1 minus 6x. And again, I just get going here. I'm not even thinking consciously of what I'm writing. It's just coming out of my mouth. So I have to stop here and go, did my brain slip a gear or not? Does that look okay? Derivative of the first times the second plus first times derivative of the second. Okay. So why is this, even though it looks more complicated, less work than foiling this out? The answer is that we need to find the slope, which means we're going to put x equals 2 in here, right? Well, put x equals 2 in here. You get 10. Put x equals 2 here. I believe you get negative 10, but you're going to have to double check me on that. Put x equals 2 here. You get 12 minus 4, you get 8. Put x equals 2 here. Well, that's a drag. You get negative 11. But can you check all 4 of those pieces for they all seem okay? So since you're going to evaluate the expression anyway, it doesn't matter how messy it is. And by the way, don't simplify this before you put the number in, because if you start simplifying it, you're running the risk of making a mistake. There's not much room for error here. So we multiply this out and add these two things together, and we get the slope of the tangent equals negative 188, I believe is what I get. The only other thing we're missing is we know that x1 is 2. We need to know what y1 is to find the equation of the tangent. So that means we need to put that value of x equals 2 into the original function. And get a y coordinate of what I believe is negative 88, but so we're putting negative 2 in for x in this expression so that we can find out the y coordinate. I might have just said we're putting negative 2. Is that what I said? If it is, I apologize. We're putting 2 into that expression. So I get 12 minus 4 is 8, and I get 2 minus 12. Well, I get negative 80? Yeah. Negative 80, not negative 88. So the y coordinate is negative 80. And now this gets tedious after a while. You're going to put that point along with that slope into your point slope formula. And I have every confidence that you could multiply that out and write out the equation in standard form. I'm not going to worry about it. Okay? It would be 188x plus y minus 1294 or something. Okay? You'd multiply it out and move everything to the other side. Won't worry about whether that's right or not. Determine the slope of the tangent to this function at x equals 1. Uh-oh. So don't do anything just yet here. Just put your pencils down and observe, because I'm going to teach you an extension of the product rule, which will come in handy later on in one of your assignments. What if I just said we have y equals a product of 3 things, which is what we have here? Well, what I can do is I can group these to talk about this being the first and this being the second, which would mean the derivative of this whole function y would be the derivative with respect to x of ab, then multiplied by c, plus a times b, then multiplied by the derivative with respect to x of c. And I hope I didn't lose anybody with that. Derivative of the first times the second plus first times derivative of the second. Okay, so then how would you go about determining the derivative with respect to x of AB? Well, the derivative with respect to x of AB is found by using the product rule. What I've just written so far is the derivative of AB. That's what this is. I still need to multiply by C. Plus AB dC. If I multiply out this C in here, this is what I get. I get the derivative with respect to x of A times B times C plus A times the derivative with respect to x of B times C. And then I have plus A times B times the derivative with respect to x of C. Everybody gets a turn at being differentiated. That's what the product rule says. So if I have three things, the derivative of the whole thing is the derivative of the first times the other two, plus the derivative of the second times the other two, plus the derivative of the third times the other two. And if there were four different terms, it would be the derivative of the first times the last three, plus the derivative of the second times the other three, plus the derivative of the third times the other three. It's the binomial theorem, by the way. That's what's going on here. And then plus the derivative of the last times the first three. And that makes this easy once you see that, because then we can find the derivative of this quite easily. Now, luckily, we are asked for the slope of the tangent. So we're not going to simplify this nightmare of algebra that's going to be created here. All right, dy dx is 8x cubed times the other 2 plus the first times the derivative of the second, which is negative 8x to the 4, times the third, which is 2x minus 5, plus the first, which is 2x to the 4 minus 3, times the second, which is 4 minus 3x to the 5, times the derivative of the third, which is 2. And now comes the time that you check everything. Okay? Excuse me. So 8x cubed, the second and the third are right. The first is right, the last is right. Negative 15. We're all going to do this. You're going to write an exam and you'll get so caught up in the calculus you'll do something like that. And then I'll go, are you sure? And you go, well, yeah. Yeah, negative 3 times 5 is negative 8. So it's negative 15. 5 times 3 is 15. Yeah, I got it now. And then my last set of terms looks okay. We're good now? Okay. So now, this isn't, I don't really like the informality of what I'm doing here, but we're just putting 1 in, right? That's all we need to do is find the slope of the tangent. That's it. This is a numerical response question. What's the slope of the tangent? And by the way, I'd already mentioned this to some people. You'll be writing certain evaluations in this course where you're not allowed to use your graphing calculator. We'll give you a little play school calculator if you need to multiply or add or subtract. but you can't use your graphing calculator on all exams, okay? So I put 1 in, and I get 8 times 1 times negative 3. This is what I'm getting at the top here. 8 times 1 cubed is 8. And I chose 1 because I don't want to waste a bunch of time doing a lot of calculations. When I put 1 in here, I get 4 minus 3, which is 1. When I put in 1 in here, I get 2 minus 5, which is negative 3. Plus, I will have negative 1 times negative 15 times negative 3. And I will double check all of these in a second. Plus, I will have negative 1, I will have 1, and I will have 2. I don't have a problem with any of those. Do you? So we work this out. What do we get? We get negative 24 plus negative 45 and negative 2. 8 times 3 is 24. 15 times 3 is 45. 2 times 1 is 2. And they are all negative, negative, negative. So that is negative 71. The slope of the tangent to this beast of a polynomial function is equal to negative 71. So let's see where we're at. That's it. So that's the product rule. Derivative of the first times the second plus first times derivative of the second. If you want, you could say derivative of the second times the first plus the second times the derivative of the first. You could say the first times the derivative of the second times the plus the second times the derivative of the first. There's all kinds of ways you can weave those things around. But you cannot go first times second plus derivative of first times derivative of second, right? You can't mix and match like that. You got to have a derivative of 1 and a non-derivative of 1 multiplied. Your assignment is from your textbook as usual. There's a variety of questions in there. I will get those quizzes either marked and back to you today by the end of class. I suspect everybody got 100 probably, but maybe not. And if I don't get them done and back to you by the end of class, then I will have them marked and recorded in Power School a little later. I'm sorry, I shouldn't have said that. I don't mean to make anybody feel bad if you didn't get 100. So get your books open, please. You got about 15 minutes here to practice this.